Welcome to our next Engineering Tomorrow session. We're talking about bridges. We're going to have so much fun with bridges, right? We're going to build some bridges. We're going to have some competitions maybe within your classroom to build a bridge that can support the most weight without breaking, right? I love this lab. I got to give a huge shout out to my buddy, Joanna Caudle. Great engineer. She's done a lot for Engineering Tomorrow. And also these students, we get college students involved because they ensure this is going to be so much fun for you, right? All about bridges. You're probably wondering, hey, Milton, you're an aerospace engineer. You're a space guy. What do you care about bridges? Well, I'm interested in developing bridges that span space. Like, is there a way to use bridges and structures to launch the next satellite or next astronaut into space? I don't know. Is there a way that we can develop bridges and structures on the moon? Maybe you are going to be the next astronaut that lives on the moon or on Mars. Maybe we're building structures and bridges for the next live like community, almost like a world that orbits around the Earth, right? Bridges are important because bridges make connections, and I want to connect us in space. Okay. So this lab is going to be a lot of fun. Let's give a little bit of history about bridges. Let's talk about bridges a little bit and talk about why they're important. First, bridges are important because they provide safe passage. If you know kind of the history of human beings on this earth, it's been very difficult for us to travel across our different continents and go across these very difficult and dangerous regions. And bridges are able to span a lot of different obstacles. You know, they actually say that you can tell how resourceful a country is or a state is, or the amount of resources and the strength of their economy just by the number of bridges they have, right? So how many bridges do you think we have in the United States? Answer that for me. How many bridges do you think there are in the United States alone? Well, if you guessed 617,000, you were right. 617,000 bridges that allow us in our country to be able to perform a lot of different tasks, for these businesses to operate, for us to secure our country, for you to be able to travel and see some of the most beautiful locations we have here in the United States. That tells you a lot about the importance of bridges, not just here in the United States, but across the world. Like, did you know that there are countries out there, there are regions that don't have access to clean water or to medical practices or to different businesses and business opportunities just because of their isolation? Bridges build connections. And this is one of the reasons why a friend of mine, I can call her a friend now, Avery Bain, developed this program to develop bridges all across the world for people who would not have had the opportunity to be exposed to clean water, to be exposed to things like the internet, right? It's just crazy. I mean, her whole business is a nonprofit to give them those opportunities. And what I think is really cool about that is you get an opportunity to use your engineering mind, your skills, to develop products that are going to improve the state of somebody else's life. Game changer, right? Game changer. Okay. And summarizing on this slide, you know, they have noticed that just by adding bridges to certain locations, their resources, their effectiveness, that region improved by greater than 30%. That's really, really nice. All right. So what's the bridge and what's its purpose? Well, we already talked about bridges span difficult locations. What I think is cool about a bridge is that you can be as artistic as you want. You can add really, really great aesthetic appeal even while you're developing a bridge that functions really well. Bridges will restore and improve infrastructure. And one of the critical things that we use bridges for is on our transportation. If I want to be able to travel, I'm from Indiana, from Indiana all the way to New York, there are going to be some obstacles I have to be able to go beyond, and a bridge is going to enable that. So what's the difficult part of developing a bridge? Well, one of the key challenges is balancing all the forces. Just like you, I mean, you're in school, you're probably balancing difficulties with social media. You got all your homework. Maybe you got some chores, all that thing causes, can feel like stress. And if the more stress you have in your body, the more force you have on your body, it can also start to feel like pressure and strain, right? And if you get too much strain, you start to feel like you're going to break. The same thing happens with a bridge. There are some tension. There's some pulling motion, right? There's some compression. There's that pushing force, and force over a certain area that's defined as pressure. And the more and more pressure that's applied to a bridge, it's going to strain. Strain is that deformation, how much it deforms, how much it bends, how much it displaces over a given region. And if there's too much strain, it could permanently break, permanent deformation. And we don't want that to happen. So as an engineer, as you're developing this bridge, you have to think about this. How do I balance all these different forces? Not just compression and tension, but even bending and shear and buckling. How do I balance all of that to make sure it doesn't strain too much? Because if people are going to be transporting across these bridge, critical assets like people, right? We want to make sure that the bridge withstands the greatest possible force that we can anticipate, mitigating the risk to people's lives for sure. Okay. So that's our bridges, and you can develop those bridges in a lot of different ways. There's a lot of different design options, and we're going to talk about this later. You see these different design options because the shape matters. Remember that shape matters. Architects, engineers are using different things like beams and suspension and trusses and cantilevers to develop a bridge that spans a given region while maximizing the amount of the strength that bridge can support the most weight that it needs to support for different things that we'll have to transport across that bridge. That's what's important. There's different engineers that get involved here. There's architectural engineers. There's mechanical engineers. There's structural engineers, right? All of them come to civil engineers and even artists, because bridges are sometimes just some of the most beautiful structures you can see, that all come together for the goal of developing a bridge that balances all those different forces. It makes you wonder, who thought of this? I just think it's really, really cool. There's a problem out there and someone engineers it, right? It always made me wonder, in the history of bridges, did someone just, maybe thousands of years ago, maybe even longer, they're standing there in some forest, they're coming to some lake, and they notice, man, this tree fell and it fell across this lake. And now I am able to walk across this obstacle that would have been dangerous for me to walk across. I always wonder, was that the first bridge? Right? So we have these bridges that kind of look like trees. And then I think engineers started to get really creative and realize we have access to other materials. We have access to concrete. We have access to stone. Now we can compile these different materials together like a composite and make a bridge that's even more, that has more endurance and more strength to support more weight. And then I wonder if they started to really realize, wait a second, we're using all these different, these heavy materials like stone and brick. What if we used a metal? See, a metal has even a greater strength for its size and for its weight. So we don't have to use as many materials if we become a little smarter with the type of material that they use. And then I wonder if they combined all those together and said, what if we use really, really great materials like metals, but also we use them with the strongest shapes like arcs and trusses to develop these bridges. So as we always ask, the next question is, what are you going to create? I mean, what's the next bridge, the next smart idea, the next smart material, the next smart shape that you can use to develop a bridge that is optimized for an even greater span, an even more challenging obstacle? Well, let's start here. Let's start with your challenge today. You're going to build a bridge, maybe as an individual, maybe as a team, right? That is going to span about 12 inches and support the most weight that you can while balancing all of those different forces. And we're going to give you a cheat code. That cheat code is the engineering design process. The engineering design process allows you to start intelligently with this design, where you think first, let me do a little research. Let me learn about this problem. Your problem is, well, how do I support a bridge, design a bridge that can support the most possible weight? And then you start with your actual design. We're going to ask that you take out a sheet of paper and really draw it out, because the better your design, the better your build. You'll spend less time rebuilding your bridge if you really think about it first as a team and you develop a good design. And then what we ask that you do is don't be afraid to fail and fail fast. After you build it, test it, and you keep testing it over and over again. I personally have been blessed to obtain a couple patents, and all of my patents were obtained from my failures. None of them came from anything that was easy. And then after you've tested and if you've passed those different failures, now we ask you to deploy it. It's time to get that beautiful banging bridge out there in the world, right? Let's expose it to everyone. It's going to be so cool. All right, let's do an activity real quick. So before we jump into developing this bridge, let's practice on something simple like some paper. So here's our challenge. I'm going to ask that you take out 2 sheets of paper, maximum 2 sheets of paper, printer paper. Okay. And what you're going to do is you're going to use those 2 sheets of paper to go across a span of about 11 inches. You'll set up some blocks or something to support your bridge that is about 11 inches apart, no more than 12. Okay. And then what you'll do with the bridge from a size standpoint, let's keep the width of the bridge to about 3 inches. All of these are your constraints. These are your constraints. Okay. This makes the competition fair. Okay. So now I want you to try to support. This is what you're going to try to support: an entire cell phone with just 2 sheets of paper. I'll give you a couple minutes and then we'll talk about it. Okay. So how did it work out? Did it work who was able to get their bridge to support an entire cell phone? Well, let me show you this and then we'll talk a little bit about what's important. Let me show you my setup. So I have a couple of wood blocks that are going to support my bridge. And the first time I tried this, I took a sheet of paper, I put it across these two spans, just something basic. I thought, well, maybe if I just curve the edges, we'll be all good. And I took my sheet, my cell phone out, and I put it on a bridge, and it collapsed immediately. And I thought, man, what do I do here? What can I do? So let's start that whole process over. When we talked about something, it's not just about the material. You can't change the material, all right? Not just about the material. It's also about the shape. So next time I did this, I took some paper and I folded it on its different ends, okay? Just to change the shape a little bit. And then I applied my sheet of paper over it. And I took my cell phone and I placed it across this 12-inch span, all right? And bam, just like that. Look at that. I can support that entire phone with just 2 sheets of paper. So that first design where I just used a sheet of paper, I didn't really put a lot of thought into it. You see, it just fell apart. But now that I use a design that was corrugated, that had a shape, that had some trusses, some triangles in there, that optimized the shape and gave it the ability to support a lot of weight. Now I'm able to support this entire phone with just 2 sheets of paper. Do you know a sheet of paper is just a couple grams, but a cell phone is hundreds of grams? The key here is that shape matters, and you can use your engineering ability, your mind, even if you're limited on the materials that you can use, to define a shape that can support a lot of weight. Let's also look at the equations behind this, right? Let's look at why are we able to do this? Okay, so here's our equations, our fundamental equations for any structure. It all comes down to like Hooke's law. Hooke's law, if you think about a simple spring, you place a force on a spring. Let's say you pull it or you push it. It's going to have a certain response. So that force is F and that response is X, but how it responds, it's all depending on K. K, that's how stiff is it? The stiffness is not just the material, which we saw at our paper demo. Sometimes you're given a constraint, you only can use one material. It's also dictated by the shape. And we just saw that if we corrugate that sheet of paper, we use those trusses, the stiffness, it went way up, right? I learned that just by looking at Amazon boxes. I cut open an Amazon box. I get a lot of Amazon boxes. And I saw all of these little curves inside of the box, these little grooves. That's corrugation. And it allows the box, which is maybe a pound, to support hundreds of pounds. Shape matters, right? Shape matters. So that's Hooke's law. And if you look at that K, if you look at the equation, what you'll see inside the equation, there's a couple variables. E, that's your modulus of elasticity. That's a tough word, right? But really, it just defines the stiffness, okay? And then L is the length, right? If the longer and longer the bridge is, that L is cubed. The more the stiffer that structure needs to be in order to support a lot of weight. And then you have I, that's your moment of inertia. That's really your shape. I changed when I took that sheet of paper and I corrugated that sheet of paper. I changed its shape. And just by changing that shape alone, I was able to support a lot more weight. And if you had to solve all of that for your response, this is the equation. And this is why you see that shape matters, right? If I can't do anything about the force, the more force you can see, a higher force means that my response is going to be higher. If I can't do anything about the length, if I have to span a really long obstacle, man, L cubed, that is going to drive the response up way high. The only thing that I really have to play with is the materials that I'm going to use and the shape. And that is exactly what you're going to play with this experiment, right? Your challenge is going to be develop this bridge, and I'm going to give you just a few different design options, right? One, we talked about it, arcs. Arcs are an extremely strong shape that you could take advantage of. If you can infuse arcs, you're going to have a strong bridge. Trusses and corrugation, like you see on this page, are also very, very important. But in the top left, what you kind of see is these U channels and I channels and L channels. There are a lot of different ways that you can place your popsicle sticks together to make these different shapes to make it even stronger. And they use U channels and L channels in bridges and structures in many of the different architectural devices that you see around. Also, lastly, I want to show you some ribs and gussets. Adding some ribs, adding some gussets allow you to take advantage of a shape that is hollow, but you still want it to be strong. You got it? So I think we talked about shapes. We talked about materials. You had a history of bridges. Let's dive right in to your challenge. Here's that challenge. You are going to develop this bridge to span about 12 inches and support the most weight that you can. You'll start by doing a little research first, right? You always want to research the materials, research bridges other folks have worked on, come up with some ideas before you design your solution. And as always, again, before you build it, really come up with a good design on paper. That's going to make your actual build much better. And then, like we talked about again before, don't be afraid to fail and fail fast. We've given you enough materials where you could build this bridge a few different times. Then after you're done, kind of analyze the results, see how well you've done, and continue to optimize. All right. So here's your challenge. And what you see on this page is a couple constraints. All right. Now, the reason we have some constraints is because it makes it fair, right? It would be totally unfair if somebody could spend a boatload of money and use something like titanium on their bridge and support 3,000 pounds. So we've given you materials that you're restricted with regards to what we've given you, simple materials, hopefully recyclable materials. And we're also saying that the bridge has to span 12 inches. That's a constraint on length, right? And we're also saying that the bridge should be, 3 inches wide, must be 3 inches wide or less. because we don't want it to be too tall, too wide or too tall. And we don't want it to have to be too short. The shorter it is, the easier it's going to be for you to support the weight. Now, you're probably wondering why constraints. Yes, it makes the challenge fair, but all engineers have to deal with constraints. I mean, if you're going to make a product that somebody actually buys, it can't be too expensive. So cost is a constraint. It has to have the right time to market. You know, if you wait 5 years, maybe nobody wants it anymore. Maybe somebody else has already invented it. So time matters, right? And then it has to have a certain level of performance. If you're going to develop a bridge, it's got to support the weight of humans and anything that's transporting across it reliably, even in weather. So it has to have a certain strength to endure those different environments. All right. That's why constraints are important. So you have all your restrictions, you have your constraints. Let me show you an example of how to set up the test. That's what we're going to see in this next page. So in this video, we're going to show you an example of how to support your cans or your weights, how to use some of the hooks that we gave you to support your bridge across a certain span. While you were watching the video, did you notice where his bridge broke? Did you? Were you able to see it? If you weren't, play the video one more time. Just rewind just a little bit. And what you're going to notice is that it didn't break in the material. This is something we haven't talked about. It actually broke where the popsicle sticks come together at the joint, at the connection. And that's important. You can have the strongest material with the best shape. But if your connections between your different beams, if that connection isn't strong, your bridge is only going to be as strong as your weakest connection or link. Isn't that crazy? I mean, the same thing goes in life. As you're working on this bridge, even with your team, you know, all your team members have to be all in and have to feel supported and valued, because, you know, if your team is only as strong as the connections, the people that you have. And I'll say this, I mean, I did talk about some patents I was able to achieve early on. They weren't alone. They were all done through teams, right? So connections, even, you know, bridges provide connections, but connections in life are important as well. Okay. So now you finish your bridge. Now you want to analyze those different results, and cost matters. So we're asking you to count the cost for every material that you utilize. You know, assign some sort of cost value to it. We've assigned some of it here. You may use some materials that are not on this page, because again, if a product's too expensive, nobody's really going to want to use it, right? So we want you to minimize the cost, and then minimizing materials as well helps us ensure that we don't tax our planet too much with some of these valuable resources. Okay. So summarizing all of this, I hope you have a blast in this lab. I really believe you will. I can't wait to see some of the bridges you all develop. Maybe you'll develop a bridge that can support 50 pounds. If you do, you just killed the bridge I developed. I'm going to have to rebuild my bridge, and we'll have a little competition to see who can support the most weight. Well, if you like this lab though, and you really enjoyed this, maybe you'll get into bridge design. But you know, if you enjoyed this lab, it's not just about bridges. There's other structures as well. There's tunnels. There's different construction materials, you know, everything that is used to develop any structure, whether on this planet or outside of this planet. You know, your engineering, mechanical, and structural design skills can definitely be utilized. And those skills apply to many different industries. There's civil engineering, environmental engineering, materials engineering, and definitely mechanical engineering, which I love. And then please, once you finish this lab, send us some videos, send us some pictures of the awesome and outstanding bridges that you created. Thank you so much for this time. And on behalf of Engineer Tomorrow, I can't wait to see you in our next session. Thanks again.